Welcome to all of you to this panel discussion on secure communication in a quantum world. So I don't really think this audience needs any introduction to the imminent threat to the public key crypto systems with the advent of quantum computers, right? And we also have a very interesting panel discussion coming up after this. So I won't spend much time on that. What I would do instead is maybe spend a couple of minutes to talk about what we are doing in quantum computing at TCS, and especially in the communication and security areas. So at TCS, we have been working in the quantum computing space for the last more than 5 years now. We have a team of more than 50 people who are working in this area, with 7 of them being PhDs. We have quite a few publications and patents in this area. And more importantly, from a business perspective, we have been engaging with around 25 customers now in various capacities and at various levels of maturity in our discussions. The work that we do at present in the computing area relates to contextualizing classical solutions with a quantum approach. So that's mainly been in the areas of machine learning and optimization. Though there are other areas like chemistry and simulations also that we have started working in now. It's also been a privilege to contribute to many of the standards activities and government initiatives, especially in India. We have a strong community of partners, ecosystem of partners that we work with. We have one of them being represented on the panel today, QNuLabs, and we are in the process of adding a few more names there, especially in the communication and security space. So this is a growing list, and even as we speak, I think we are at mature stages of discussions with some of our future partners. The work that we do largely relates to experimentation on various computing quantum platforms that are available today, uh, both gate-based computers as well as annealers. A lot of the work that we do, especially in the research area, relates to benchmarking of performance and trying to maximizing performance on the current NISC hardware. Resource estimation is another area that we are working in, and we are also looking at the possibility of creating some IP in that space. The work that we do on the business front largely relates to working with our customers who we treat as partners and help them in their journeys of quantum exploration. We are working across all the 4 areas, although as I said, machine learning and optimization is what we started with largely. And we have been fairly new entrants in the security and chemistry space. A few of the customers that we are currently engaged with actively, that is what is shown below. So moving on to security and communication. So as we can see at the top of the slide, the secure communication market, the QKD market, is projected to grow to almost 5.3 billion by 2028 at a CAGR of almost 20%. A quick glance at the table on the right. So while both PQC and QKD have their own merits and strengths and weaknesses, as you can see, QKD is something that is promising to deliver security that would be omnipotent, it would be long-term, it would be robust, and it would be unconditional. Right. There are 2 main approaches on the QKD front. So you have the continuous variables, where we use to measure information encoded in the properties of electromagnetic fields. And on the other hand, you have discrete variables in which we measure information encoded in polarization of each photon. From our perspective, we are currently focusing on the continuous variable space. So in the telecom industry, if you see the fiber optic communication systems are already equipped for CV encoding and decoding measurements at 1550 nanometers wavelength. And hence employing CV QKD protocols can be quite cost effective. So we are working on building demonstrators in that space, which we believe would be of immediate interest to our customers. CV QKD protocols for the IoT too seems to be something that would have near-term commercial viability. So that is another area that we are actively exploring. On the other hand, scaling QKD systems over intercontinental distances in free space may require discrete variables QKD, employing single photons. But that also requires larger investments, and that is not something that we are looking at this point in time. QKD's technology readiness can be well gauged from various successful long distance implementations over metropolitan networks, which countries like China, UK, and US, among others, have already implemented. Right. As well as the rapid productionization by various product-based companies, some of you which you see there on the screen. As I said, we are happy to have had opportunities to participate in and contribute to several Indian standardization activities, both in the QKD space and PQC space. We do have a detailed point of view which is there on our website, and I invite all of you to visit and have a look at it for more details on our work in this area. With that, I would once again welcome you to the panel discussion and hand it over to Shomo to carry the panel discussion forward.
Yeah, thank you, Vidyut, for the nice introduction about what TCS is doing in this quantum technologies. Now I will invite all the speakers one by one. So Vidyut, can you share the screen?
Have we got the right view, Soumya?
Right. So yeah, so all the speakers are here. So first, starting with Mr. Andrew Lord. Andrew joined BT in 1985 after a BA in physics from Oxford University. He is currently leads the BT's optical core and access research, including optical access, high-speed transmission, and quantum communication. He was technical program chair for OFC 2015 and general chair for OFC 2017. He will be TPC chair for EOCC 2013. He is editor-in-chief in Journal of Optical Communication and Networking. And he is a visitor professor at Essex University. He is fellow of the IEEE and a BT distinguished engineer. Welcome, Andrew.
Thank you. Hi.
Right. Now I will introduce Dr. Ho Jing Yan. He is currently quantum communication technologist in the National Quantum Safe Network at Center for Quantum Technologies, National University of Singapore. With more than 10 years of experience in quantum science research, his current responsibilities include deployment of quantum key distribution devices, security validation, standardization of quantum safe technologies, and collaboration with industries and government agencies. Hello, Dr. Jing Yang. Welcome.
Hello. Yeah, good to be here.
Now coming to Thomas Stengel. He's a senior director business development globally for ID Quantique devices for quantum enhanced security. ID Quantique harnesses light to develop and industrialize advanced quantum products and technologies for organizations to ensure long-term protection of data and public safety. With a background in R&D, marketing, and sales, and 25 years of experience in semiconductor processor and artificial intelligence, today the focus is on semiconductor-based quantum technology and the specific use cases. Welcome, Tom.
Thank you very much, everybody.
Now coming to Professor R.P. Singh. He's a faculty member in Atomic, Molecular and Optics Physics Division at Physical Research Laboratory, Ahmedabad. His research interests include light scattering, nonlinear optics, singular optics, and quantum optics. He's leading the Quantum Science and Technology program in PRL in India. He was involved in the demonstration of entanglement-based quantum communication over 300-meter free space channel, along with real-time cryptographic applications. Hello, Professor R.P. R.P. sir, you are in mute.
Hello, can you hear me now?
Right, we can hear you.
Thank you. Thanks.
Now coming to Sunil. Sunil is the CEO of QNuLabs. The company has developed India's first commercially really quantum security product and solution. He holds a degree in computer science engineering from NIT Trichy. He's a business leader and an entrepreneur with 30 years of experience with specializing cutting-edge technologies. QNuLabs has won prestigious awards like NASSCOM's Emerge 50 and League of 10, DSCI Most Innovative Product of the Year, and National Technology Award for Startup with Commercially Ready Indigenous Technology, National Startup Award 2022, and IDX Defense Innovation Organization. Hello, Sunil.
Hi, thank you so much.
Right.
Everyone. Yeah.
So welcome to the panel discussion. Now I will ask question. So as there will be audience who are not from the quantum technology background, quantum communication background. So coming to Professor RP, who is an educator. So RP, can you briefly tell our audience that why we need quantum communication? What are the drawbacks of classical communication and how does quantum provide an advantage?
So classical communication, there is no drawback as such. We are doing pretty well. But because as you told in the beginning, because of threat from quantum computers, our present day algorithm, which makes our present day communication secure, that will be threatened. That will be compromised, present day encryption system. So that's why we need this quantum key distribution, which is one of the applications of quantum communication. Okay. So in quantum key distribution, basically we make key and distribute the key using quantum mechanical principles. And even quantum computers cannot break that encryption because our keys are based on key we distribute and generate. That is based on quantum mechanical principles. So there is no threat even from quantum computing. That's why we have to go for quantum key distribution. Otherwise, classical communication, we are doing good, except quantum computer threat from quantum computers. We have to go for this quantum key distribution, one of the applications of quantum communication. So that is the thing, and basically you communicate through quantum state. When you say quantum communication, you are communicating through a quantum state. Instead of classical bits, you are using Q bits, which are superposition, which is very typical to quantum mechanics. Qubits are basically superposition states. Instead of 0 and 1, they are like superposition of 0 and 1, means both are possible at the same time. Existence of 0 and 1. One system can be 0 and 1 at the same time. So it's very peculiar to quantum mechanics, which is not possible in classical. So use these kind of states, and that gives you advantage, lot of advantage in making your communication secure. There are no cloning theorem. Such states cannot be cloned. Okay, so that is the advantage you get when you use this quantum key distribution. Somu, can any I have
Yeah.
forgotten. There are so many parts of the question.
Yes,
Have I
sir.
addressed all the parts of
Right.
question, or I have missed
Yes,
something?
yes. Right. So you have addressed all of the parts of the question. So we have the theoretical background about this quantum communication. Now, having this theoretical background, I will come to Dr. Ho, who is from application background. So, Dr. Ho, can you tell our audience that what are the most promising application and use cases of quantum communication, and how this technology will change the way we approach communication in the near future?
Yeah, thanks, Sonia. Absolutely. So I think as what we can see right now, quantum communications technologies is actually one of the most mature quantum technologies. So we have seen, I think just now there was also in the intro, some of the examples intro of the quantum key distribution companies, quantum communications companies. So a lot of these technologies are already starting to become off-the-shelf devices. So I think, yeah, here I will probably just mention a few key examples. So the first one will be the quantum key distribution, where we, as Professor have mentioned just now, so by utilizing the quantum properties, a quantum key distribution system allow two parties, space-time separated, and then they can distribute a pair of symmetric keys among them. And these symmetric keys, because it's utilizing the quantum signals to share the key, so any eavesdropping attempt of this channel will necessarily leave a fingerprint, and this eavesdropping attempt will thus be detected by any parties that are communicating. So a quantum key distribution system will allow the communication system to have this, to enjoy these secret keys that is protected by quantum physics. And we definitely starting to see this being used in multiple sectors, such as government, comms, financials, health sectors, and also more sensitive, let's say, military aspects and so on. There's also another technology. I think the quantum random number generators is very similar to the quantum key distribution, but usually for myself, I'll call it that you have the source and the receiver in co-located, let's say for a simple quantum random number generators, where because of the intrinsic randomness of the quantum physics, and one can actually utilize it as an excellent candidate for randomness generation, which is can be probably to be secure and unpredictable. Going to the questions of changing the way towards near future quantum communication, I think first and foremost is really for us to address the quantum computing threat. That's why we need this quantum safe communication approach. So starting from the quantum key distribution with randomness provided by probably quantum random number generators. And then after these first steps, I think there are also more advanced technologies such as teleportations, entanglement, distributions, and so on. I think maybe later on we will have some time to look at them.
Yeah, thank you, Dr. Ho. So now we have the theoretical and practical knowledge of quantum communication. Now we go that where it is implemented. So BT and Toshiba launched first trial of quantum secured communication services, and EY became the first customer to connect quantum secured data connection between major London devices. As Andrew was involved in this project, so Andrew, can you tell us how quantum communication technologies be integrated with our existing classical technology infrastructure, and what are the potential benefits and limitation of this integration?
Yeah, it's a very good question. I think the first thing to say is that quantum or QKD has moved to the point of being commercially available, and so our implementation just looks like any other network implementation. It's not an experiment, and that means that all of the management of the quantum network that we've built is part of our existing network infrastructure management. So if an alarm goes off, if a QKD device fails or issues an alarm, that is picked up by the general BT network data management network. And that has to be the case. If you're building QKD as part of your existing infrastructure, you have to integrate it at the point of even the alarms, the failures, the resilience. So that's the first thing. The second thing is you have to build networks. It's not enough just to build a point-to-point quantum link. Okay, that would be good for some customers, but generally, if we want to see this being taken on board across the whole of a country, such as India or the UK, you need a network, which means you need 10 or 20 or 30 quantum nodes, all interconnected with a key management system that sits above, making sure that all the keys from the different QKD devices go to the right places. And so that your overall QKD network supports dozens of customers, 10s, 20, 100 customers, all on the shared quantum infrastructure. That's what we're trying to explore in the London network.
Yeah, thank you, Andrew. So we have the knowledge of how quantum communication can be incorporated with the current classical communication technologies. But we know that quantum computing or quantum communication required a new type of devices, right? And ID Quantique is working in this type of devices since 2001. So Thomas, can you tell us that what are the major challenges being faced in the development of quantum communication devices and how these challenges being addressed? And what is the current state of the art?
Yeah, so I think you need to break that into pieces a little bit. As Dr. Hall was saying earlier, it's not just quantum key distribution and PQC, it's also quantum random number generation. And as Andrew Lord was saying, we talk also, it's not just point-to-point QKD, it's heading toward QKD networks, quantum networks, and eventually down the road, quantum internet, which is going to involve the being able to network with qubits. So each one of those four pieces have their own challenge. So in the case of the QRNG, as Dr. Howe was talking about, that has been commercially available for more than 2 decades. But more recently, in 2019, it got shrunk down into a semiconductor device. So when I look about the challenges there, the next set of challenges being new to the semiconductor space is the traditional semiconductor things, adding capabilities while reducing power consumption and reducing price. And that's well underway. So that set of challenges has led to it being used like anything from cell phones to satellites right now today, automobiles and stuff. When we look at QKD, I think Andrew Lord already talked about the next real major step is the trusted nodes and being able to build it out into a more, go beyond point-to-point QKD into QKD networking is the next major step. And for PQC, PQC is in it's in its shakeout period. I think we've already talked about QKD has been shipping commercially more than 10 years. QRNG has been shipping commercially more than 20. PQC, there are some people with products and are shipping them, but it's definitely in its shakeout period. The spec itself is technically not even complete yet. So I think the next challenges are really to get through the shakeout period and have those algorithms be verified. And then after that, in order to be cost effective, it's going to have to transition from software implementations into like a semiconductor implementations. And there's already people who are already working on that, and we're taking the risk that the current versions are going to make it through the process and stuff like that. So I look at all those, each one of those things has a different challenge on its curve to being more available around the world.
Right. So, yeah, so given that we have discussed the major challenges in the development of commercially viable QuTe product. So, Sunil, so can you kindly share, you are the pioneer of QKD companies in India. So can you share how you are overcoming these major challenges and what is the state of the art?
Yeah, thank you, the panelists, very wonderful insights. So as we all know that QKD, short distance QKD has a very limited value, right? A pure point-to-point QKD. So I would answer this question saying that there are 3 key dimensions in which we need to implement QKD in order to get some real value creation, right? First is a long distance QKD. How do we get QKD either through trusted nodes? How do we take it to 1,000 kilometer, 2,000 kilometer? So that is the first area we addressed. And today we have trusted node and QKD, where our single hop is 150 kilometer, and then we can add trusted node, and we have already done about 400 kilometer trials, and then we are now planning to do about 800 to 1,000 kilometer. Right, so that is one area where you start seeing use cases, right? Interesting use cases. Now, second dimension is what Andrew talked about. You eventually want to create networks, right? And starting with metro area networks. So you need to have topology where instead of point to point, you should be able to create hub and spoke, star networks, and so on, right? So how can we take a point to point QKD and we build a hub and spoke? So that's what we did. Second thing, we went ahead and built a hub and spoke where one hub can connect to multiple spokes. It not only reduces the cost of the overall QKD deployment, but then it also allows one spoke to talk to other spoke through hub without having a direct connection between them, right? And then it also opens up several very interesting use cases, specifically where you have one control station and trying to communicate with multiple satellite stations, right? And then the third point which comes up is, which is very, very important, that QKD is not an independent system, right? QKD network is a overlay system that works in conjunction with the existing crypto equipment, right? So it is very important and pertinent that the right interfaces are developed. Like example, a QKD, as Andrew was again saying, you connect QKD boxes not on the physical layer, but you ought to also connect them into a management layer, right? Where they can be connected to a northbound interface management interface that could be an SDN controller, where you can manage the network as a software-defined network, right? You don't want to see with advent of QKD, while it brings a certain value, it removes the value of the software-defined networks that it brings, right? So it has to be evolved in a manner that it has a interface to SDN controller. And then, of course, the other important area is that how do we move away from proprietary interfaces to more standard interfaces, right? For example, key event, when you QKD generates a key, how do you distribute this key to other routers, encryptors, right? So at C014 that you have to implement, right, that you do. Then there are the key management layer that you have to build either in your QKD, or there's a key management product that node available in the network. So you have to make sure that you have built a key management or delivery layer where all the keys that you're generating are not stored at QKD. You ship them out to a key management system, and all the encryptors and nodes will continue to collect keys from key management system. And those, so you're not changing the existing architecture of the way the classical cryptography works, right? And then in the process, of course, you have to, as a QKD in the commercial, this thing, QKD in itself has to be a system that cannot be hacked, right? You have to make sure that it doesn't only do a man-in-the-middle attacks, take care, which is a fundamental use case of QKD. But then we have to also make sure that it is secure against the theoretical quantum computer attacks like photon number splitting attack, and then intercept and resend attack and so on, right? All the 4, 5. Besides that, there are several side channel attacks are coming up. So we have to ensure that all the side channel attacks are taken care. That is where we will get a really relevant QKD product and solution, which is robust, which can deliver keys to a longer distance and can create cost-effective networks. So we tackled all three dimensions in order to build, and that is what we are trying to deploy today.
Yes, Sunil. So yeah, so whatever you are telling is true. So we have to take care of these attacks, right? So now coming to RP. So RP, we know, as Vidyut told, that there are two ways to realize this secure communication, free space and fiber based. So can you elaborate that? How to compare these two ways, and what are the advantage and disadvantage for our audience who is not directly from the quantum side?
if you want to have intercontinental quantum key distribution, then both are required. That's what I feel, because intercontinental connectivity can be achieved through satellites, then fiber to fiber you can. So you need to integrate satellite-based quantum key distribution with fiber-based. So both have to be there. It's just not like fiber, just not satellite-based. Okay, both existence of both is required, and both are having advantage and disadvantage. Like when you are doing satellite based, it has to be line of sight. Okay, you have to have ground stations which can pick up the signal sent by the satellite. If you have ground in such a place where satellite cannot see, you can't do. Then some denial of service, somebody, like if you know that satellite is going to give the signal, something can pass by, it can denial of service easily can be the denial of service attack can be taken. That way fiber is there, you can cut the fiber, denial of service there also one can do if you are doing with fiber. So what I feel, existence of both is both are important, and both have to like join together to have secure communication, secure quantum key distribution. They have to complement each other. One has to learn how to relay from free space to fiber, fiber to free space. So that should be the scenario instead of just fiber or just satellite. Although both independently can be done, you can have like suppose you want to cover India using satellite based, you can have 130, 140 satellites. So you can have continuous coverage of ground station all over the India. You can have number of ground station, you can have number of satellites, yeah, and you can have continuous. This is costly affair. And then suppose cloud is there, some weather is bad, signal will be poor. Then fiber can be helpful. Same way fiber, maintaining the cost fiber is very high maintenance, yeah, making them work all the time. So those are the problems. And as everybody knows here that fiber quantum signal, you're sending quantum state, you can't amplify the quantum state, so you can't send it very long distances. So those are the shortcomings of the fiber. But I think both have to be there, and both have to complement each other for secure quantum distribution.
Right, RP. So in line of this answer, so we know that we need both fiber and the free space communication. And as Vidyut introduces, so there are two ways also to realize this quantum technology. One is the discrete variable based, and another one is the continuous variable based. So can you again tell us that in which of this application we need this discrete variable or the continuous variable, and compare their advantages and limitations?
So, as you told, continuous web QKD, certainly it's easy to integrate with existing optical communication network because you are using homodyne detectors. So current homodyne is already done in optical communication. So it's easier, and you don't require single photon detectors. Homodyne detection is good enough. Gradually, security issues are also being sorted out with the CVQKD. Earlier, people were scared that regarding security of QKD for longer distances, but that is also being addressed now. And there are like theoretical results that even with satellite, one can have CVQKD. Not only like metropolitan area, and that will remain secure. So only time will tell like whether CVQKD will prevail or discrete variable QKD will prevail. Um, Discrete variable looks like much more intuitive when it comes to quantum thing. Quantum communication, quantum key distribution. Discrete variable is much more intuitive. You are sending photon, it's a quantum mechanical entity. You are measuring photon, so it's much more intuitive. While this continuous variable is not so intuitive according to quantum mechanical system. Okay, But it also uses discrete continuous variable, also uses quantum mechanical principles. So
Right,
we're
right.
measuring field quadratures. Okay, but it's not general public. It's not so science general,
Right,
like
right,
who is
right,
interested in science. For them, it's not very obvious that it's
right, right, right.
quantum unless until you talk of photons. So those things are there. So only time will tell which will prevail, continuous variable or discrete variable. But continuous certainly much practical and cost effective.
Yes, Professor RP. So yeah, we know that we need continuous variable and discrete variable. So I think there are audience who may think that current age is the internet age, right? So what about the quantum internet? So I am coming to Dr. Ho. So Dr. Ho, can you tell me that what is quantum internet? So and when it's going to come, and what is the state of the art, and what are the current challenges in realizing the quantum internet?
Yeah, thanks, Somya. So I think maybe first thing that we need to understand is quantum internet itself is different from what we are has been discussing here, quantum networks, where in quantum networks, what we are doing typically is that we are sending classical information on top of quantum signals. And then if this quantum signal is being intercepted, then there's this alarm system that Andrew mentioned just now that will trigger and so on. For quantum internet, what is being sent is actually quantum qubit, quantum bit itself. So meaning that we are now sending a much more delicate information, so to speak, or a signal over across this network. And there are more work that is needed to be done in order for this qubit, so-called, to be propagated around this network. So maybe let me illustrate further. So for the qubits, when they are being sent over, we can no longer use what we, let's say, typically use in quantum network, such as trusted node, because once you detect the qubit will become a classical signal, and you can no longer use it for any quantum operation. So for the quantum internet, is a network where people are seeing qubits are propagating live, can also be entangled, correlated, multi-partite states. So they can be propagating throughout this network. And then some of the use cases, including, for example, quantum teleportation, where you can actually teleport the quantum state without sending the quantum state across, the state to be teleported across, just by sharing entangled states beforehand, for example. Then there are also use cases such as distributed quantum computing. So if there's a way to share these qubits across different nodes, then they can also perform some joint operations, for example, or coordinated measurements and such, to allow for quantum computing applications. But to realize all this, as I have already mentioned just now, we can trusted nodes and something wouldn't be useful. So they are one of the main challenges that I can identify, I think, would be, say, a quantum repeaters, where what is being repeated is really the quantum qubit itself, not the classical signal. And this will certainly extend the range of or the lifespan of these qubits as they propagate throughout this quantum internet. And I think another aspect that needed to be addressed is how this quantum routing going on once such a technology was made available, because surely there will also be different type of protocols or scheme that could be realized should there be to such a network exist. Another main thing is what we call quantum memories. So because the quantum state, as we share them across, there's also a need to time synchronize and process the information over, let's say, for two different parties, so that they are actually addressing and looking at the right quantum states. So there's also a need for quantum memories in this situation, for example, to allow for these synchronizations. And we see, yeah, all these definitely will still require quite a fair bit of R&D, but we are also seeing a lot of tensions and also a lot of funding being put into realizing this next generation of quantum networks. Yeah. Thanks.
Yeah, thank you, Dr. Ho. So we have a nice overview of this quantum internet and quantum memories and everything. Now coming to Andrew, so you have implemented this quantum communication in London. So what are the other ways to efficiently adopt this quantum communication, and our general public or our maybe interested to know that after this quantum communication, what are the actual uh, problems will arise, right? So, or if it will be better than our normal day classical communication, or it will be same, right?
I mean, exactly the same. So a typical provision for a customer will be an Ethernet service. So a standard SME or a bank or an industrial customer, probably not a residential customer at this stage, to be honest. This is going to be a company that has, requires secrecy, requires a security. They will purchase Ethernet connections, for example, 10 gig Ethernet, 100 gig Ethernet, as before. That they just need to click a button saying, I want this to be a quantum secured Ethernet provision. Alternatively, maybe they want secure access to the cloud, in which case their access to the cloud will be exactly the same, maybe running over an IP channel. But this time, instead of just standard IPsec, we will add a quantum key distribution element on top of that to make sure that that whole entire communications channel is now quantum secured. But as far as the customer is concerned, it looks the same. And the equipment that we use, so the Ethernet equipment that we use is identical, with the difference that it's got an external key input. So the encryptors that we use have got the facility, and we buy our encryptors from Thales, but you can get them from others. They have an external key input way, so you can feed in the QKD key from your key management system on top of any inbuilt key distribution security that the equipment has. So a typical HSM will already have Diffie-Hellman RSA style encryption. Maybe in the future we'll have post-quantum built into it as well. We will leave that. That's completely, fine, and we shouldn't change that. What we want to do and what we're doing is adding a QKD element on top via an external key. As far as the customer is concerned, it looks identical.
Right. And regarding the cost, so the general public always worries about the cost. So whether internet will be more costly, whether our telephone will be more costly, whether the communication or the the calling we are doing, the calling will be more costly. So what will happen for that?
So yeah, I'd say the reason we're doing the trial is to look at two aspects. Firstly, there is the access, where you have a dedicated link to a customer. That link is not shared by anyone else because it's a fiber link that goes directly to a customer. Clearly, it can't be shared. That is short. It's probably 5-10 kilometers, and that's an access fiber tail, which carries everything. It carries the Ethernet data plus the key encryption. When that fiber access link comes into an exchange building or a central office, for example, a BT central office in London, that then is combined with multiple other access tails coming into this quantum node, and all of the keys are aggregated. And the keys that are used to encrypt all of those different customer access tails are sent to the right destinations via the key management server. And that means that our metro network shares all of the access traffic. So in other words, the customer doesn't pay for a completely dedicated end-to-end quantum link. He has to pay for the access element, but then the rest of the network is shared. So it should be much more cost effective. But what I will say is that access element could still be very expensive. We do need to think very carefully, how do we build a QKD system for short distance, for example, 5 kilometers or 10 kilometers, where the performance is not, it doesn't have to be fantastic, it just has to be good enough to secure a dedicated access over a very, very short distance. And that's where I think continuous variable QKD could really have a big part to play, which is very, we've already heard discussion of continuous variable, but I think it could be more cost effective in terms of implementations over those short distances.
Right, Andrew. So, so as we know that yeah, quantum communication, quantum devices may be costly, may be cost effective, but there are other people from classical communication, from classical side. So they came up with this post-quantum cryptography that Tom and Vidyut has earlier told, right? So Tom, coming back to you again. So all our discussion is coming to this quantum technologies, quantum communication, but someone from classical side, they can say, okay, I can give you security, I can give you everything you need in quantum using this post-quantum security, post-quantum cryptography. So can you give a comparison that somebody, so which one to adopt, this post-quantum cryptography or this quantum communication, right? So what are the security limitation in PQC and the security limitation in QKD?
So first, I'll say that I believe that they're going to coexist for a very long time. Maybe, you know, the first thing is about the longevity, the long-term confidentiality. You know, PQC is brand new; it's going through its shakeout, and even during its early shakeout, two of the algorithms experienced problems, which may or may not prove to be fatal. And so, you know, we can't. You know, Julius Caesar used Caesar squares, and it took centuries before the Roman army discovered somebody could break them. I don't think we can count on that with the rise of quantum computing. The question is, how long will any particular PQC algorithm live? And of course, we're designing them to live forever. That's always the goal. I think PQC and QKD must coexist because QKD is a physical implementation and PQC is an algorithm, and there is always the issue. Algorithms always fall eventually. There's no such thing as, you know, we are unlikely to be as lucky as the Roman army was to have an algorithm last for centuries before it was broken. And so I think if you're deploying a system, you're going to have to do both. And they both offer some, I mean, of course, one is encryption and one is a physical distribution of the key. So they're not identical. But in terms of quantum safe implementation, I believe they'll both coexist for decades.
Right, Tom. So, yeah, so now the initiatives are coming from industry. You are working with government sector, with industry, with academia. So can you tell us that how academia, industry, and government can collaborate in co-harnessing quantum communication ecosystem, and what should be their strategies?
This question is for whom? Soumya, we lost you actually in between.
Yeah, Soumya, we lost you for a while, so maybe you
Right.
quickly want to repeat the question and.
Right. So Sunil,
Okay.
we know that you are what? So can you hear me now?
Yeah, we can hear you now.
Right. So Sunil, you are working with academia, industry, and government bodies, right, for co-harnessing quantum communication ecosystem. So can you tell me that how academia, industry, and government jointly can implement this quantum communication, and what should be their individual strategies?
Yeah, so obviously, as we understand that all the three parties, government and startups and the academia, all three have a very important role to play. So the way we are seeing this panning out, right, in the last couple of years, the government becomes the impetus, right? They have a particular critical infrastructure to protect. They have a particular applications to protect. So they are the ones who need to come up with not only funding grants, but they have to also come up with important use cases. So we are working with government to identify very pertinent, useful use cases, which once implemented successfully can really trigger, right? Many use cases, and it can be like it shouldn't lead to another one only. It should lead to hundreds of new things. And an interesting part is that different than the common understanding, most of the use cases in government and defense are actually an enterprise use cases, right? Once you implement them successfully, you can very easily take those and implement in any of the public enterprise, right? And private enterprise. For example, people are talking about securing networks, right? It could be Wi-Fi networks, it could be fiber optic networks, and so on. So you can build today a hybrid solution using QKD. Of course, QRNG is given, right? Is a root of trust. And then you can build a QKD plus PQC, depending on how critical link is, right? And you can build a very good hybrid mesh networks, right? Which are very, very important. I think that is where the government role comes in. That if they don't take an initiative to protect their critical infrastructure applications data, then it will not initiate, right? Now, where the academia comes into picture is that the government gets confidence not from startups, right? Largely because they have to invest money. They get confidence once it is basically validated, endorsed, or some sort of a early demonstration is shown by academia saying that yes, this technology is feasible, this is possible, and yes, this can be implemented, right? Once that happens, that is where the third entity come into the picture, which is a startup company like us, who's then going to bring a commercially viable system, right? Which can be packaged into a box, which can have right interfaces, which can withstand the hacking, which can withstand the noise, ambient light, whatever else is required, right? Other specifications quickly. So once you bring that together, that is where the real impetus comes in. And fortunately for India, we have seen all three happening. The academia has been very active, the likes of Professor Singh. We have seen Indian government defense taking a huge interest, right? And then fortunately, we also have ready products, right? Which we are able to create a lot of valuable use cases and case studies, which are now being taken out for mass deployment, right? So I think each three of them have a very important part, and a good understanding and I would say the collaboration leads to success.
Yeah, right. Thank you, Sunil. I think our audience have a now clear understanding whether they are coming from government side, from academia side, from industry side, that what are their roles and what they need to do to contribute this quantum communication thing. So this is the end of the question from my side to the end of the panelist. Now requesting the audience, you can post your question and we will try to ask this question to our panelist. Now there is a first question. This is related to software engineering. So Vidyut, so I'm asking this question to you. So this question is that my question is about the position where we software professional with 10 years of experience and knowledge on quantum computing can fit into the quantum industry. Vidyut, you're on mute.
Yeah. So my take on that is, see, a lot of the development which happens in the quantum computing area, okay, it is hybrid in nature, right? So it requires a mix of quantum development as well as a lot of classical development. So a good place to start probably is getting an exposure to quantum computing, working in those kinds of areas, right? And then depending on your interest levels, your motivation, it is all up to you as to how deep you want to go in the quantum computing space, right? But there are opportunities. There are opportunities for all kinds of people. There are opportunities for quantum physicists, mathematicians, engineers, quantum specialists, as well as the traditional software developers.
Right, Vidyut. Thank you. So coming up the next question, Sunil, this question is for you. So Pramita asked this question. So what is the scope for the new startup companies to work in quantum domain, especially in QKD?
Yeah, I mean, the second or third generation of QKD systems are coming up. I mean, the new companies need not invent. right? For example, ID Quantique started in 2000. They built the first generation of quantum QKD. The companies who came later didn't have to reinvent what they have done. They went into they started developing the second generation of QKDs. And now I think there are a great opportunity for new companies to startups in QKD to look at newer protocols that are coming up, right? And then, as it was said that I think the real challenge with the QKD right now is to how do we bring down the cost to $50,000, right? For a pair. So then you have to work, and if new startups can take up those challenges, they don't have to solve the other problem because there's enough paper, patents, information that is available. So you can quickly work on a QKD, but then take up on newer challenges which are available, right? So I think there is a scope, definitely a scope for new startups.
Right. Thank you, Sunil. So coming up the next question, Thomas, so you can answer this question. So what is the best way of using post-quantum encryption and QKD for satellite communication?
So the best way of using it, I will say, so the technology already exists in chips in different ways. In terms of the QRNG, there's already chips certified for space. In terms of post-quantum cryptography, there's people who already have algorithms, and QKD. So people already have implementations for at least the post-quantum cryptography where they're trying to run them in FPGAs. So the hardest part about going to space is not just taking the technology, but you have to make sure the technology can survive in space, the radiation and all of that kind of stuff. And that's already, of the three pieces, if you will, QKD, PQC, and QRNG. The QRNG certainly is already accomplished, and the QKD is also to a degree already accomplished. So I would say that it for PQC, I could guess what their roadmap to space is, but I have not actually seen anybody publish it yet. But I would suspect their roadmap to space is going to be to run PQC on an FPGA that is already certified to work in space. But I have not actually seen anybody implement it. But that's really what it comes down to, is taking existing implementations and implementing them in electronics that can run in space. There's a limited, as an example, there's not an unlimited number of processor choices or FPGA choices or various other component choices to run in space. So you might have to redo some of your existing engineering to make it run on a different processor, as an example, if you do something in a processor in order to get one that works in a satellite.
Right. Thank you, Thomas. So, Dr. Ho, you are also working for satellite communication in Singapore. Security is doing some satellite communication. So, can you add some points for this answer?
Yeah, certainly. So, as you mentioned, in Singapore, for Center for Quantum Technologies, there are satellite QKD research, and then there's also a spin-off from the university called Spectra, looking at quantum communications over over satellite. I think the one way to do it is also to execute, for example, PQC on the satellite itself. That shouldn't be an issue, provided the computational bandwidth and so on that is required can still be supported. I think there's a recent preprint or publication that is from our center. So I will encourage the research, the person who asked this question to have a look at it. And for QKD, yes, certainly for the satellites, there's a lot of active research over there, and also deployment to see how we can really utilize the satellite to bring QKD not just at the terrestrial level, but also across global network and also beyond, for example, typical prepare and measure system, but also at, say, entangled photons and so on. And we are seeing a lot of developments there.
Thank you, Dr. Ho. So the next question, Andrew, I think you take this question. So what kind of exigence is expected in telecom industry in terms of timeline to adopt quantum communication system? Should CV be a better choice over DV for securing office campus or banking sectors?
I think we're going to see some very significant changes in the next 2 to 3 years. The first one is going to be when the mainstream telecom vendors, such as Nokia, Cisco, Huawei, Fujitsu, Ciena, Adva, all of these guys produce, or some of them produce a QKD or a quantum network edition of their own, which means that then operators like BT will find it very simple to go and buy quantum-enabled communications when we need it or when our customers want it. It will just be an additional card plugged into existing telecoms equipment. We can't do that at the moment. At the moment, we have to do our QKD from a completely separate vendor, but that will change. And I think it's going to change very soon. And the question around CV, I think, is very relevant, because I think that mainstream communication vendors like Cisco, Ciena, etc., will find it much easier to implement a CV QKD solution into their existing telecoms equipment. So I think that is the first major transformation we're going to see, I predict, within a year. The second one is more like 2 years to 3 years when we have satellites. And satellite QKD distribution then allows global connectivity, global secure connectivity. That's also close, but not quite as close. Once those two things happen, I think the whole area is going to be transformed, and we will find CV QKD cost effective for access, inbuilt into regular telecoms equipment, and then you'll have the more complex, maybe the higher performance BB84 or satellite or entanglement-based protocols to do the national and the international connectivity, all within 2 to 3 years.
Yes, yes. Thank you, Andrew. So next question is a bit more technical. So RP, can you take this question?
We have to be a bit careful about the times. So I'm
right.
not sure, because our panelists might.
Right. So there are 3 more questions. So we'll take this first. So RP, so is measurement device independent security also an impressive requirement for realizing QKD in banking and telecom sectors?
It's better to have not only measurement device, you can have device independent completely. That is the safest way to have QKD. You don't depend on device imperfections. But getting sufficient key using device independent QKD protocols is the challenge. Once it is overcome, that will be the best thing to do for any secure communication, when you don't depend on either source or detection site. So that is the best thing to have. But there are limitations right now. But as technology is improving, it's good. Days are not very far when you will have very good key rate for device independent QKD protocols.
Right. So there are 2 more questions. So we take it those very fast. So any input on quantum sensing? So Tom, can you take this?
Yeah, sure. So the quick, you said quickly, I'll do the quick version. Quantum sensing has been commercial viable for many years. So the real question is, where will it help quantum communications? And when you get to quantum networks and the quantum internet, when we start talking about qubits themselves being transitioned, that having detectors, having really high-end quantum sensing gear is going to be part of making successful quantum internet gear. And that technology already exists. Certainly, there's always there'll be future improvements and performance and cost and stuff, but that technology already exists.
Right. So this is the last question. So Vidyut, you can take this question. So Dhruva Shaw, so he said, while I was explaining the quantum technology to my CSC friend, they asked one question: how this gonna affect their way of programming in a software? Vidyut, you are on mute.
Okay. Yeah, so I'm not really very clear about what specifically the answer the person is looking for. So again, Programming could be at various levels, right? So one is as a Python programmer, probably there are a lot of things that a person would be able to do on quantum computers. Okay, but at a deeper level, yeah, there is a fundamental difference on how you would go about programming a classical computer versus a quantum computer. So which is where a deeper understanding of quantum technologies would be required. So yes, if you want to make that shift from a classical developer to a quantum developer, at least in the current era, there would be some amount of learning that will have to be done, some unlearning to be done. Maybe over a period of time, some of these things might get abstracted and the differences might become minimal as we go along.
Right. So our time is almost over. So thank you all the speakers. So now I request Vidyut for his quick closing remarks.
Yeah, thanks, Soumya, and thanks to the wonderful panel for this very stimulating panel discussion. So before thanking them for their thoughts and their insights during the discussion, I would also like to sincerely thank all these panelists for their contributions to the field. I think each one of you was a pioneer and a stalwart in your own ways, right? And we are really happy and grateful that you could take some time out from your busy schedules and spend some time with us and participate in our efforts to celebrating today's World Quantum Day. The audience, I think the panel covered a vast range of topics, right from the need for quantum communication to the readiness of the telecom sector for quantum communication, to the current challenges in scaling this over large distances. And I'm confident that the audience would have been able to appreciate the rapidly growing technology of technology readiness of quantum cryptography and its applications over various verticals. I'm hopeful that today's discussion will foster greater collaboration across industries between academia and industry in the days to come. And probably this also serves as a stepping stone for more such engaging sessions in future. I would also end by thanking the audience. I think it's been a wonderful audience and some of the questions have been really interesting. And last but not the least, thank you, Soumya, for moderating the session. Right. And once again, wish all of you a very happy World Quantum Day. And hopefully this will be a decade of quantum. Yeah.
Yeah, thank you.
It's going to be century of quantum, not decade.
Century of quantum. Yeah.
Right.
Thank you, Vidit,
So-
Soumya, and everybody. Yeah.
Thank you all the
Thank you.
panelists. Thank you,
Thank
RP, Sunil,
you.
Andrew, Tom, and Dr. Ho. Thank you everyone for joining.
Bye-bye.
Thank you.
Bye.
Okay, thanks.
Thank you very much.
Bye.